Very good then.
Yeah.
I will begin the talk.
Thank you.
As Luis was mentioned, my name is Gordon Shaw. I work at NIST in the Mass and Force group. I'll be talking today about the electrostatic force balance and its applications in small mass and force measurements. As I'm sure everyone's aware, the SI was redefined in 2018 to be based on fundamental physical constants. And for mass and for force, this manifests as a change from the primary standard being the international standard prototype kilogram to the primary standard being either the Kibble balance or the Avogadro sphere for the kilogram unit of mass. After the primary realization, we have to disseminate the mass measurements out into industry. And so this path takes the form of the primary realization here at NIST on the Kibble balance, and then a vacuum to air comparison between the working standards and the primary the standard kilogram measured in the Kibble balance, and then to get to masses smaller than 1 kilogram, a process called subdivision is used, where groups of masses are compared against each other to reduce the mass value that can be calibrated. I have in this graph on the right I show the value of mass in kilograms on the x-axis. On the y-axis, the uncertainty in that mass. As you can see, the uncertainty in mass increases as the mass is subdivided further and further. One of the advantages of the SI redefinition is that we can realize mass at any scale. So in our case here at NIST, we developed an instrument called the EFB, or Electrostatic Force Balance, that measures mass using electrical quantities. So similar to a Kibble balance, except the Kibble balance uses an electromagnetic force, whereas the electrostatic force balance uses an electrostatic force to measure mass. And at the milligram level and below, we can realize substantial reductions in the uncertainty. So the red circles are subdivision uncertainty, and the blue squares here are the uncertainties we can get in mass on the EFB, and this is about a 1 milligram. You can see we have an order of magnitude lower uncertainty here. The way that this balance works, I have a picture on the left here. I have highlighted in green here the moving part of the balance mechanism, and on top here is what would be our mass pan. So this is where a calibrated mass would be placed, or another force that we would like to generate. And we compare the weight of this mass to the electrostatic force generated at a capacitor down here at the bottom of this moving part of the balance. And we can use this measurement equation here to determine the mass using measurements of capacitance, position, voltage, and local gravitational acceleration. Capacitance is traceable through the quantum Hall effect to fundamental constants. Displacement is measured using a stabilized helium neon laser interferometer. So this can be traced to the hyperfine splitting frequency of cesium-133 and the speed of light. Voltage is traceable to a Josephson junction array, and local gravitational acceleration is traceable to an absolute gravimeter. So because we have all of our quantities are traceable through the SI to these fundamental constants, we have a direct link to the fundamental constants in this instrument to create a primary realization. And several other institutes around the world have started doing work on these kinds of balances for small masses using electrostatics. If you're interested in finding out more, I have a paper in Measurement Science and Technology from 2018 that reviews some of these new developments. However, these developments are not solely confined to the world of mass. There are other measurements that also benefit from the ability to measure small forces and small masses. And I'm going to talk today about a few different places where the SI redefinition has improved our ability to do other kinds of measurements other than just measuring mass. So the first one I'm going to talk about is a standard reference material that was developed here at NIST for atomic force microscopy, or AFM. The atomic force microscope is an instrument that uses a microfabricated force sensor with a sharp tip and is brought into contact with a sample surface. The forces between the sharp tip and the sample allow us to either map the surface topography with nanometer scale resolution, or to apply very small forces from piconewtons to micronewtons on the sample to measure mechanical properties at the nanometer scale. Typically, the probe that is used in atomic force microscopy is a cantilever, AFM cantilever, and I have a picture of one here. And you can see it's about 400 micrometers in length in this case. And it is microfabricated typically from silicon, and it's treated as a reference, as a spring. So it follows Hooke's law. So if you can measure an applied force and you can measure the displacement of the cantilever as it bends, you can calculate a spring constant out of what I call K here. And then this K can be used as a way to measure the force if we can measure the bending of the cantilever beam. And unfortunately, these are very small, they break very easily, and so you cannot use a reference mass to calibrate these cantilevers. How do you ensure accuracy in these types of measurements? There's an ISO standard, which is a documentary standard. There is a big data approach that John Sater in Australia has, where he's collecting data on all different kinds of cantilevers that you can use to compare your measurements against other people who use that particular approach. And then finally, there are reference devices. So this would be a reference cantilever that has a known spring constant that can be compared against. And this is the approach that NIST is taking at the moment. We have developed a standard reference material, SRM 3461, that is an array of 7 of these cantilever reference springs that are shown here at the end. These small rectangles here are the cantilever reference springs. And they're microfabricated by NIST in the Cornell NanoFab clean room. We have about 90 of these that have been produced, and they provide a spring constant reference that's traceable to the International System of Units. And we get our traceability using the electrostatic force balance. You can see here, this is a large-scale picture. You'll recognize this is the electrostatic force balance I showed earlier. And we have a sharp probe tip here. And these small objects here are the reference cantilever arrays. What we can do is we can bring this sharp probe tip into contact with one of the cantilever springs. We can apply a known force using our electrostatic force balance, and since there is a known displacement from the laser interferometer, remember the spring constant is the force divided by displacement, we have all we need to generate a traceable spring constant. So we've done this for the cantilever devices, a subset of the cantilever devices, and we compare that against other methods. So in NIST, there's a laser Doppler vibrometer method that measures the thermomechanical vibrations of the AFM cantilever to calibrate, to measure a spring constant. And our two methods agree within 1%. Also in industry, Asylum Research has measured the spring constant of our AFM cantilever reference material using their quadrature phase differential interferometer. And that agrees also within 1%. So we get sub-percent agreement within multiple different laboratories using multiple different methods, and in some cases multiple different sets of physics. So we're fairly confident that this can be used to generate accurate measurements for these atomic force microscopy measurements. This SRM is now available if anybody is interested. It can be bought at the NIST shops, and it's commercially available for research. Moving on, I want to talk now about another measurement that is of another quantity within the SI, that is laser power, and how we use the electrostatic force balance methods to get a traceable calibration of laser power. In this method, what we do is we use a phenomenon called photon pressure force. when a laser beam reflects from a surface, it generates a force. And this force can be calculated, this force can be used to calculate laser power using the measured force, the speed of light, and the reflectivity of the mirror. So the idea is that we have a laser source, we reflect off a high reflectivity mirror, and measure the force that is generated from the photon pressure force. And in this case, at this 45-degree angle with a high reflectivity mirror, we get about 5 nanonewtons of force from 1 watt of laser power. And this, there is a NIST reference device called the radiation pressure power meter that does this, but we calibrate this with masses that are measured on the electrostatic force balance. But we thought it would be cleaner if we could provide a direct traceability pathway to the fundamental constants using a balance to directly measure the radiation pressure force. And so here is an electrostatic force balance that we built here at NIST and deployed at a NIST boulder that has a high reflectivity mirror fixture here where the laser can reflect. And then we have a capacitor at the bottom to generate a traceable reference force. And so the idea is that we can directly compare the electrostatic reference force to the photon pressure force generated by the laser to calibrate the laser power. And we use this instrument in conjunction. Here is the electrostatic force balance here. It's in an enclosure. We have an instrument called the HALO, which is the high amplification laser pressure optic. And this is a set of high reflectivity mirrors that allows us to reflect the same laser beam 12 times on the mirror on the EFB. So this multiplies our force by a factor of 12. So we get a slightly larger force, which helps with our uncertainty. And so we are interested in measuring high laser powers between 1 and 10 kilowatts. So this might be for laser cutting, welding, and those kinds of industrial processes that these calibrations are of interest. So some sample results here, just showing that we have, this is the force measured by the electrostatic force balance, and you can see when we turn the laser on, the force changes, and then we turn the laser off, it changes again. Keep in mind, this is about, here in this case, I believe that this is about 5,000 watts of laser power, and you can see the balance is very, very stable, so thermal effects are not affecting the balance. And what we see is a combined standard uncertainty of about 0.12% in this measurement. And what this allows us to do is actually get an uncertainty that's lower than the current measurement standards. Here I have a transfer standard that is used. It is a thermal pile transfer standard. And the uncertainty is shown in the error bars here. You can see that the statistical uncertainty from the thermal pile is much smaller than the statistical uncertainty from the electrostatic force balance. The difference here is that there are systematic uncertainties in the transfer standard from the calorimeter used to calibrate it. And so what we have here is, by doing a lot of averaging with the EFB, our uncertainty, I'm showing the uncertainty in terms of as a function of the number of averages here that we are doing. And you can see that the uncertainty drops as a square root of n. So we can actually reduce our statistical uncertainty by averaging because the balance is so stable. And that because our systematic uncertainties are much lower than that of the existing calorimeter primary standard, we can actually provide a lower uncertainty. And so in summary, we designed a balance to measure laser power using photon pressure force. And we shown that there's a potential for the improvement in the uncertainty by directly realizing the force in situ to measure the laser power. And work on this area is ongoing. Finally, I'd like to talk a little bit about a project we have to measure radionuclide activity. And this is through a project called the True Becquerel at NIST. And this is to update our radioactivity measurements here at NIST to accommodate new technology that's been developed. This is, an important area because we have concerns for security, the environment, nuclear medicine, for cancer therapies, and electronics that all depend in some way upon being able to measure radioactivity for accuracy. And if we have something like a radiopharmaceutical, it really, really needs to be right, because you could have adverse impacts upon people's health if your standard is wrong. So it's critical that we get it absolutely right. In these kinds of projects, we're interested in the SI unit of radioactivity, the becquerel. It's a derived unit and it describes the number of radioactive decays for a particular decay pathway for a particular radioactive isotope. And so this is I should say the average number of decays for a particular isotope. In the real world, the most common way that these standards are disseminated is using a liquid solution of a radionuclide salt. So the radionuclide element or isotope is dissolved in a liquid, and then the liquid is measured out by mass. And for a given amount of material, the given mass, a radioactive activity in becquerels is specified, so that when this standard reference material is used, in the final calibration environment, the SRM can be dispensed by mass and then used to determine the total radioactivity in becquerel. So these SRMs come with an activity concentration in units of becquerel per gram. And my job in the project is to be able to measure the mass of the liquid for these radionuclide activity measurements. And the design concept of this is to create a balance. And this all here is our balance mechanism and our capacitor that we use to generate the electrostatic reference force. And to this balance, we attach essentially an inkjet printer head. So we can dispense liquid from this inkjet printer onto a radioactivity sensor. And by measuring the change in mass as we dispense the liquid, we'll know exactly how much of the liquid is dispensed. So this will be a primary reference balance, once again, to determine the mass of the liquid sample from voltage, capacitance, and position measurements. We've constructed this balance at NIST, and this is a picture of it. And you can see it's a little difficult to see right down here, but the inkjet dispenser is down underneath the balance here. And this is the reference capacitor at the top. Preliminary measurements have been done using a wire mass that we calibrated here at NIST. We see that in this case, we're able to measure the mass of the wire with less than 0.1% standard deviation, relative standard deviation. The accuracy is also less than about 0.1%. And so this work is in progress. We've demonstrated that we can do this for a wire mass. Now we are working on demonstrating that we can do the same accuracy for a liquid sample. And we're working on various strategies, including eddy current damping and acoustic treatment, to reduce our noise and improve the uncertainty. Okay, so in conclusion, the redefinition of the SI has impacted areas other than just mass metrology. What we've seen is the electrostatic force balance can be used to calibrate standard reference materials for small force measurements, such as this standard reference material 3461, which provides an accurate standard for a nanometer scale mechanical properties measurement. We've also constructed new balances, and in this case, we have another balance that's constructed to provide a primary calibrations for kilowatt laser power using the photon pressure force. And what we've seen is that this photon pressure force actually, we can do these measurements with better uncertainty than the current standards that are used potentially. And so this could be a way to improve the uncertainty in laser power calibration. And then finally, we have a balance that was constructed to provide traceable mass metrology for liquid samples of radionuclides. And these materials are of broad interest in a broad segment of industry where radioactivity needs to be measured. And in some cases, it's extremely critical that the measurements be absolutely correct. We constructed this balance and are in the process of testing it for the use in measuring the mass of liquid that has been dispensed by the balance. I want to acknowledge some of my colleagues here, the NIST Mass and Force Group, the NIST on a Chip program, and the National Quantum Initiative at NIST. Both are providing funding. My graduate students and postdocs, Sven Schultz, Kumar Arugamagam, and Lorenz Keck, and also some of the project participants in the True Becquerel project. It looks like I might have some extra time here. Is that correct, Luis?
Hello. Yes. Yes.
Okay. So maybe I'll go through and find something else here that I wanted to share. Let's see if I can. I don't know if it's in this presentation. One moment, please.
Yes. No problem.
Just describe briefly here how we're doing the measurement of radioactivity for the True Becquerel project. In this measurement, the mass is only sort of half of the measurement. So I've outlined a little bit about how we're using the electrostatic force balance to measure the mass of a dispensed fluid. And so once that is we dispense the fluid, we dispense it onto a gold foil sample. And in this case, the reason that we're using the electrostatic force balance rather than a larger scale balance or something like that is that we need to have a very small amount of liquid. The sensors that we're using are I'm showing a schematic of one here, are called superconducting transition edge sensors. And these are a few millimeters on only about, say, maybe 1 centimeter total in a square centimeter total in area. And they require a sample that's about 1 square millimeter. So they need essentially a microliter of solution dispensed. So that's about 1 milligram of an aqueous solution. And the way that this works is we dispense this onto a gold foil, and then we place the gold foil on the superconducting transition edge sensor. The superconducting transition edge sensor is essentially a very, very sensitive calorimeter. It can measure the heat energy from individual radioactive decays. Interestingly, it can also measure the energy of the decay process. So the two things that we need for this measurement to realize the Becquerel here are the number of decays per second, the average number of decays per second, and we have to identify which decay process is occurring. And because these sensors can measure energy, they are able to measure which decay process is occurring as well as how many of them there are. And so this gives us all in one shot all that we need for a realization or to characterize a standard reference material. And so this is a way to greatly simplify potentially the production of these reference materials, and also to do radionuclides that might otherwise be difficult to do with conventional methods. And with that, I think I will say Many thanks to the organizers for having me at CLUB de la Balanza, and I'll be happy to take any questions that you have.